Hello, everyone. My name is Bhaskar. I am very excited to come forward with this brief lecture on time series forecasting. Starting with the short story. In the movie Lagan, the protagonist tries to forecast the rain by looking at black clouds. We always thought black clouds were representative of an incoming rain. Somehow it doesn't work until the end of the movie. Funny side aside, there are sophisticated ways of forecasting anything in this planet, and we will try to cover some basics in this brief lecture. So here we go. So let's talk about forecasting first. Well, this lecture also assumes that the student has already gone through basic statistics and advanced statistical techniques, including certain prediction techniques like linear or logistic regression. Linear and logistic regression talk about predicting an outcome. They, with a predefined set of factors that are already in place, they can tell what is the probable outcome of a certain situation, whether it is in the future or it's going to happen right now. If that such a if such a sophisticated algorithms already exist, what are we looking at forecasting here? Why exactly a separate topic is carved out just to understand forecasting alone? So let's talk about very quickly. Let me define what the difference between prediction and forecasting as we see on the screen. A prediction is a statement which tries to explain a possible outcome or future event. Forecasting refers to a process of looking forward and predetermining future trends. So forecast, in a short sense, forecast is only looking into the future. Prediction can be anything. It can be an outcome. So broadly, prediction is a superset out of which forecast is a subset. Let me take a small example here. If I were to measure the average annual temperature of a particular city for the past 100 years, as you can see on the screen here, there is a certain graph which has been plotted, which shows on the x-axis the year and on the y-axis the average temperature that was captured. So there is a certain graph that is plotted which with its own ups and downs. Now, if I want to say what exactly is the influencing factor for temperature, then I'll have to think of various factors that even cause temperature. For example, forest cover. Depending on the amount of forest cover at that locality, temperature may be higher or lower. The kind of industrial growth that we see in that place. If there are more industries, there is more pollution due to which the temperature may go up. The number of vehicles that were put on road in that year. If there are too many vehicles that come onto the road, which have a lot of carbon monoxide and sulfur monoxide gases coming out of it, they also cause temperature, and buildings constructed. So if I have to write the temperature as and what are the factors influencing it, it would be a function of all these various factors, which we can see on the screen. So in the same way, but this will only tell me what are the functions that have caused the temperature at that particular year. But what is the crucial thing that is being missed out here? Yes, the temperature graph itself. What exactly is the memory that is hidden inside this particular graph? What are the various trends and seasonalities, or anything, any nuance that is in this graph which we have not uncovered? And that is exactly what forecasting is going to tell us. It is going to bring out these beautiful flavors that are hidden inside the graph and show it to us, and then help us forecast into the future. But there's one important observation you need to make here. Forecasting doesn't need for us to understand all the factors influencing temperature here. I don't need to know forest cover or industrial growth or vehicles, etc., to be able to forecast. All I need is the temperature that was there in the past 100 years, and that's it. With the algorithms that we're going to talk about right now, we should be able to forecast into the future what the temperature could look like. And that is the beauty of this. So to be very short, as I have already said before, prediction is a much bigger term, out of which forecasting is a subset of it. Forecasting will help come up with a particular value that is going to happen in the future by looking at the values that have happened in the past and nothing else. So that is exactly what it is. Next, so what are we forecasting here? We are forecasting using data. And what is this data? This data is called time series data. Normally, if I am collecting data at a certain time period, for example, I'm calculating the temperature of a sick patient every 1 hour for the entire day. That is that process of collecting data every hour is called a stochastic process. And the output, the data that comes out of the stochastic process, is a time series. So very simply put, a time series has only two columns: one, a time; two, a value against each time. In a much more technical term, this is actually a univariate time series, wherein which there's only one particular variable that is being displayed against the time, which is what is the focus of this lecture as well. So we are only talking about univariate time series. So yes, the output of the stochastic process is a time series. So a few more words on the screen is a sequence of measurements on the same variable collected over time. Univariate if only one variable is involved. The measurements are made at regular time intervals. If I were to make the temperature measurement at 12 o'clock, 1 o'clock, and then at 3 o'clock and 4 o'clock, that is not a time series. A time series needs to have data collected at regular intervals and not at irregular intervals. Next, the observations that are being captured should be chronological. So there is a meaning to why the time has to be chronological, and the importance of this we will understand when we are actually forecasting. Certain examples of time series that I'm bringing up so you can appreciate what we are talking about. The first thing, monthly precipitation in Portola, California. It's a small city in California from January 1999 to April 2004. So on the x-axis, there is month. So this is monthly precipitation. So for the entire month, what is the total precipitation or rainfall that has happened in that city? So as you can see, the data has been collected at regular intervals and for one factor, which is precipitation only. So that is a good candidate for time series data and even for forecasting. The next example, there is population of USA from 1900 to 2000. So this is also captured every year, population of US captured every year over course of 100 years. So this is also a good time series. What is not a time series? It is also important to know what is not a time series, so we don't fall into the trap of building models which are worthless. So for example, look at this particular example of the Dow Jones Index, the Dow Jones Market Index for various different companies, MMT, AXP, BA, CAT. On a certain day of September 2012, this particular data has been captured. Now, this is not a time series because it has been captured only on one day and it is captured for various different companies. So this is a bad example of a time series. This is simply a cross-sectional data and not a time series. So when a time period is not the same, that is, for example, as I said here, ATM transaction volume is interspersed with quarterly volume, the data set cannot be called a time series. So yes, so I think this will give us a good understanding of what is and what is not a time series. Moving forward, just giving a brief of what time series application, where all can it be applied for? Budget analysis. Budget analysis is a very good factor where time series can be applied. Every year, many countries come up with their own budgets. So looking at the past 50 years of budgeting, the amount that has been budgeted, we can come up with what the government will budget for the next year. Seismological predictions, weather forecasts, inventory management, financial market analysis. The stock market is one of the best examples of where time series can be used pretty well. Not that it will give a fantastic prediction, but still one of the very good ways of predicting into what is going to happen in the next few hours or the next day, etc. So moving forward from here, right? So before we even start forecasting, we need to understand what a time series constitutes of. A time series data. What does it have in it? What is that a hidden meaning inside it which we want to unearth? So that is what is called time series analysis. When we are analyzing the data, it's called analysis, and once we have a good hold of what is in it, we will be at a better position to forecast it. So let's try to analyze a time series data. So quick notes here. So modeling, you want to model a time series for descriptive or predictive purpose. So it is not only the fact that we would like to use time series modeling to do only forecasting. We could even understand what is actually there for now. But yes, forecasting is a good way of using time series. We could also find, yeah, as I said, descriptive or predictive. So in order to describe or analyze a time series, it can be decomposed or split to understand the trend and seasonal factors. So I have spoken about two terms here, trend and seasonal factors. Both of them mean what the words say. So what is the trend that we are seeing in the data, and what is the seasonality we are seeing in the data? To understand it better, I'm going to switch over into R and analyze a certain data set. Let's see how it looks like. Okay, so I have the RStudio open in front of me. I have taken up a data from beer production, quarterly beer production in Australia from a certain for a certain period of 18 years or so. So this is a data which is in an Excel sheet. I'll give you a quick look at how this data appears so you can appreciate what is the time series. So look at this Excel sheet over here. So it has only two columns. The first column is basically the year and quarter. The second column is the number of what do you call million liters of alcohol or beer that has been produced in that quarter in that country. So I've imported this particular data into R, and I'm reading that over here. Okay, so I have read this data into R. Looks like it's a bit slow, but there you go. So the data has been imported into R successfully. Next, I'm going to use an XTS function to basically define what I have in this particular data set. I'm going to say to R that the first column is year and quarter. So I'm going to use the XTS as.year quarter function to do that. That is done. Next, I'm going to plot this particular XTS variable, see how it looks like. So there you go. So this gives us a good picture of how this time series data appears. As you can see, it basically constitutes of looks like a sinusoidal kind of a series. It's going up and down and up and down, and then there seems to be an increasing trend over here. So very simply put, as we can see, the production has obviously increased over the course of 1956 to 1974. And there seems to be certain level of seasonality here on certain quarters. Every year on certain quarters, there seems to be a spike, and that seems to be the seasonality factor here. So it's a very what we are doing right now is just visualizing the data and seeing what is there. So broadly, we can see it has increased. The trend is increasing, and there seems to be some level of seasonality in it. To understand it even better, let's try to use functions that are built for this purpose. I'm going to use as.ts function to convert it back to a time series, so as to be able to use decompose functions on top of it. I've done that, and now I'm going to use the decompose function. All right. So look at this particular graph that has been outputted after we decomposed the time series. So on the top is actually the observed data. This is the same data that we have seen in the earlier graph. The next one is the trend. So trend basically is coming up with the way in which it shows the mean values at every point. And as we can see, the overall production of beer in Australia over these years has increasing. So that is the inference we should get out of it. And seasonality, you can see this is the seasonality at every quarter. We at a certain quarter every year we are seeing that is spiking in up and down. So after taking into consideration both the trend and seasonality, anything that is left out is putting into this random function. So there is no explanation to this. Now the beauty, so trend and seasonality have been put out, so we were able to see that even without using this function, but still we know what the numbers for trend and seasonality are. But the randomness is where we should be spending more time in. The randomness in most of regression related topics, we assume that the output random residual has no correlation with. But in this case, that may not be the in time series, that may not be the case. There could be variables where there could be random residuals which are autocorrelated, and that means there is still some more information or some more juice that can be extracted from these random residuals, and that is something we will also cover in a few minutes. Okay, so a quick look at the values of the decomposition. So as you can see here, so if I see what these values look like, so these are the observed values, the first one. Next is the seasonal values. As you can see, more or less the seasonality is there. So at quarter one, and there is it's so much, and then it's going up in quarter two, coming down in quarter three, and again going up in quarter four. So there are spikes in both quarter two and quarter four. So that is seasonality we're seeing. The trend we are seeing has been an increasing trend. Has always been going up and up and up, and ultimately the most in the end. And these are the random numbers. So the same thing that we have seen in the graph is what we are seeing here. Okay, so now moving forward, so we have also used a certain function called additive type here. Now I'm coming back to my presentation here. So we didn't speak about that aspect, but I'll explain that right now. So the decomposition that we have done right now is additive decomposition, which means the overall observed values are assumed to be a sum of the trend, seasonal, and random variables. So that which means that if I am adding at a particular point, if I'm adding all these three values, I'm going to get the overall output value. And it can be assumed that an additive decomposition can be done if we see that the seasonal variation is constant. If we see that the seasonal variation is increasing over time, then we will have to use the multiplicative decomposition, wherein which the output variable is a product of the trend, seasonality, and the random variable. So in this case, we have seen that the seasonal variation is constant, hence use the additive concept. Okay, so coming to the next one of the other objectives of decomposition is to estimate seasonal effects that can be used to create and present seasonally adjusted values. So for instance, look at this example here. In many regions in the US, unemployment tends to decrease in the summer due to increased employment in agricultural areas. Thus, a drop in the unemployment rate in June compared to May doesn't necessarily indicate that's a trend towards lower employment. To see whether there is a real trend, we should adjust for the fact that unemployment is always lower in June than May. So what it's trying to explain here is that the reason why we decompose to pull out the seasonality and the trend factors is that if there is a seasonality factor, we should not wrongly assume that there is a trend change as well. It need not be. It's only the seasonality might not actually cause a change of trend, and that is exactly why we should decompose and understand it, a time series, before jumping into much more the forecasting techniques, etc. So we spoke about decomposition. Let's talk about smoothing. I will increase the font on this a bit so you can see better. Oh, I guess it's not taking it. All right, so smoothing is also another way of analyzing the time series, wherein which we smooth out certain factors like seasonality to be able to see the trend better. So this is also another way of analyzing the hidden meaning that is kept inside the time series data. So one of the most well-known ways, even before time series forecasting methods were even invented, moving averages method was a very popular way of smoothing out time series data. So for example, at a certain point, the moving average will be the data of the next quarter, the data right now, and the data of the previous quarter averaged together. That is the moving average at that point. And then when you go to the next point, the moving average will shift, will move to the next point accordingly. So this is a moving average. So by doing this, it will smooth out any level of seasonality, and then we will be able to see better patterns and understand what is going on in it. And the next example of smoothing is single or double exponential smoothing. Basically, what it says, if you can look at the equation that I'm trying to highlight right now, it says that, let me, I guess I'll have to, oops, I'm sorry. Fine. It says that at a particular point, the observed value is a function of the previous values in time. So xt plus 1 is a function of xt, xt minus 1, xt minus 2, etc. And if you can see, the coefficient that is used here is exponentially decreasing. So we are saying that the value right now is heavily influenced by the immediate predecessor, much less influenced by the one before it, even lesser influenced by the one before it. So that is what exponential smoothing. So you are exponentially reducing the weightages of the previous occurred values and its influence on the current value. That is what is called exponential smoothing. It's exponential smoothing it also helps in doing one-step forecast. As you can see in this equation, it says xt plus 1, which is actually doing a forecast of the next step. It's actually a very good way of doing forecasting into the immediate next quarter or the next year, depending on the frequency of your time series. A double exponential smoothing when there is can also be used when there is trend but no seasonality. So as you can see, essentially the method creates a forecast by combining exponentially smoothed estimates of the trend and the level. So two different weights or smoothing parameters are used to update these two components each time. So in the earlier case, we are only using alpha and then exponentially reducing it. In the double exponential smoothing, we are going to use two different factors, one for the trend and the other for the level, because there is no seasonality. And the way we tweak these factors is what will give us the smoothing effect. So that only comes with experience, but this, we're only introducing you to all this stuff. So fine. So we have been able to understand what is a time series, understood what is forecasting. Now let us try to do forecasting. What are the best ways of doing forecasting? So when we talk about time series forecasting, two great statisticians come into picture. They are George E.P. Box and Gwilym Jenkins. In their landmark study in 1970, they came up with a bunch of time series models called AR and MA models. They are also called Box and Jenkins models. So these models basically cover up, try to take into consideration the trend, seasonality, the autocorrelation within the variables, and the ways in which one can model time series data to come up with good forecasts. So one of the first models they describe is the autoregressive models. Now, very simply put, an autoregressive model is more or less like a single exponential smoothing model. But the way we do it, if you look at the image that I've posted over here, so it's a two-step process. Okay, the step one basically is we capture the trend and seasonality in series. So the trend and the seasonality that is occurring in the time series, we can capture it either by regression. You could use linear regression to capture it, or we could use smoothing effects, the single or double exponential smoothing, or we could use the differencing factor. So now by using all these methods, we could do a forecast into the future. Once that is done, we have the residuals left, which have autocorrelation in them. Now, when we have the autocorrelation on the residual model, on the residuals that are left out, we try to come up with an autoregressive model. We try to come up with a way in which these residuals are influencing the residual errors are influencing the error that is being forecasted. So the forecast of errors is what we get in the step 2. And so when we put step 1 and step 2 together, we get the error of errors, which is the ET minus ET hat. So we already got the forecast errors from step 1. We got the forecast of the forecast errors from step 2. By putting these two together, we will be able to come up with a way in which we can forecast to the future. I'm going to go a bit more deeper into this in the next slide. So the autoregressive model, which is the first model proposed by Box and Jenkins, basically says that the current value of an observation is a factor of the previous P lagged observations. When I say P lag, P can be 1, 2, or 3, or anything. What it means is if P is equal to 2, it means that the beer production, if we go back to our example of the beer production in quarter 2 of 1975 is a factor of quarter 4 of 1970, quarter 1 of 1974, quarter 4 of 1973, and quarter 3 of 1973. And there is also an intercept and a error factor which is introduced in it. So if you look at this equation here, that's exactly what it's talking about. Okay, now this along with this is simply the autoregressive aspect. We are only regressing the variable with itself. That's why it's called autoregressive. And then the Box and Jenkins came up with another model called the autoregression and the moving average model. Now, what happens in this model is, along with the autoregressive factor, they are also adding an additional set of lags of the errors. That is why, and these are called the moving average components. So basically the idea is to capture all forms of correlation by including lags of the series as well as the forecast error. So we have the moving average, the autoregressive terms, which are the YT minus 1, YT minus 2, YT minus 3, etc. And we have the forecast errors also as part of the model, which are epsilon t minus 1, epsilon t minus 2, etc. And depending on the number of lags we want to go there, epsilon t minus q as well. So the ARMA model, by defining what is p and q, we can come up with a decent forecast explaining the output. And finally, the ARIMA PDQ model. In this case, he's coming up with the statisticians Box and Jenkins are stating that by first applying the differencing on this one and then applying the ARMA model will bring out the better results into our forecasting. So that's exactly what it is they're stating here. I guess you can see the image that we are trying to show. Sorry about that. Yeah, there you go. So the first step is to apply differencing on this on the data. Differencing can be done at 1 lag or 2 lags, and that is also there is a way to the way we get to these numbers is also very important. And once the differencing is done, then the ARMA model is applied to come up with the forecasts. That is what is called the ARIMA model. So it's very important to know exactly what these PDQ values are before even coming up with and to actually tweak these values well, and which comes only with good experience, and only then the forecasts will be appropriate. Finally, I would like to talk quickly about how we validate the models that we have come up with. Model validation, usually for any cross-sectional data, it is 80-20 or usually 80-20. 20% of the data is set aside and 80% is used to build the model, and on the 20% it is being tested. But in this case, it is very important that the 80-20 that is being selected is chronological. That means if there are 100 points of data, the last 20 is what should be set aside. In cross-sectional data, any 20 is fine, but in time series data for model validation, it's important only the last 20% of data is set aside for validation. The remaining 80%, which is also chronological, has to be used for model building. So, and once the model is built and tested, it can appropriately be forecasted with the necessary confidence intervals. So with that, I would like to end my lecture here. Thank you, Great Learning, for giving me this opportunity. It's been a long time since I have taught anyone. So this has been an exciting journey. As you have rightly said, it is helping me learn as well. So thank you. Have a good evening.